Good day and welcome to CFE Media's virtual training week. For this session on short circuit protection for variable frequency drives, we'll be joined by Steve Peralt, Drives Product Manager, Low Voltage Drives, Yaskawa America. I'm Kevin Parker, an editor with CFE Media and Technology. Following our presentation, be sure and stay tuned for the live Q&A. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. A certificate of completion will be available for each participant to download upon successful completion of a test at the end of the presentation. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. Widespread use of variable frequency drives in many industrial processes makes it more important than ever to understand how UL standards and testing relate to VFDs. This session will outline typical system requirements for short circuit protection of variable frequency drives, as well as address the issues involved. Here are some of the learning objectives of today's session. Here are some tips to help you get the most from today's session. If you are experiencing issues with the slides or audio, refresh the browser or click the Refresh Media button. Control the volume of this webcast by adjusting the volume on your computer or the webcast platform. For technical problems with audio or the slide presentation, click on the question mark at the top right-hand corner of the screen. If a technician is needed, type a message in the Ask a Question box. The Ask a Question box is also used to ask questions of our speakers. The live Q&A session will begin after the presentation concludes. Today's session is being recorded. You will receive an email within a week with the link to the on-demand event. The exam will be posted on CFE Media websites with the on-demand version of this webcast. The exam is for one RECEP ASIC Certified Professional Development Hour. Before turning to our presentation, we'd like to share a brief video from today's sponsor. Welcome back. I'd now like to introduce today's speaker. Steve Peralt is the Chief Product Line Manager for Low Voltage Drives at Yaskawa America. Steve has over 30 years experience in the automation industry, specializing in the variable speeds drive market. Steve is also a NEMA committee member. Steve, welcome to today's virtual training week session, and please go ahead.
Thanks very much for that introduction, Kevin. Hello, everyone. I'm happy to be here with you all today to discuss protection of drives and related UL approval. Our goal is that by the end of this session, you'll understand enough to confidently select short circuit protection methods for drives. With that said, let's get started. So looking at the flow of topics for today, we're going to talk about short circuit protection, the what, why, and how, typical scenarios for protecting drives, these two terms that often get confused, which is short circuit current rating and amps interrupting capacity. We'll talk about the evolution of the UL standards and the impact on testing for drives. We'll look at an example of manufacturer's instructions to make sure that protective devices are properly applied. And we'll wrap it up with a summary followed by some questions. Let's start with the basics of short circuit protection. First of all, let's look at this thing called short circuit current. A main concern when connecting equipment is to understand how much current can flow in the event of a short circuit. As of 2020, the US National Electrical Code standardized on the term available fault current. And available fault current is simply the largest amount of current capable of being delivered at a point on the system during a short circuit condition. And I'll stress at a point on the system. As you can imagine, there are many different points on the system, and available fault current at any given point is highly dependent on the voltage and the impedance of the supply system. So if you were connected, for example, directly at the output of a transformer, you would have very high fault current. And if you were connected at some point down the line where you have cable impedance, etc., your available fault current at that point would be much less. Okay, that helps us understand what fault current is, but why do we care? Well, we care because, number one, electrical equipment has a wide range of ability to withstand short circuit energy. They're not all the same. Not all equipment is the same. Secondly, if there's improper selection somehow, it could result in a very dangerous situation known as arc flash. And even without opening an electrical panel, this can happen. It can expel large amounts of energy. Temperatures can reach very high temperatures, and it can throw projectiles. It can cause normally grounded surfaces to become live. Now, those are some pretty good reasons to care about available fault current, but what does a person do about it? Well, complete elimination of danger is near impossible for most things in life, but we can certainly greatly reduce risk. Fortunately, there are helpful rules to follow. Most installations are subject to national electric codes, such as the NEC for the US and the CEC for Canada. And these codes specify that you must protect your branch circuits. And so that's branch circuits or wiring up to the equipment. And in some cases, it also protects the equipment. But often, there's also supplemental protection that's required when what's being used to protect the branch circuit wiring does not actually protect the equipment. Additionally, the equipment must be chosen such that the withstand capability, or the short circuit current rating, is greater than or equal to what's available for fault current at that point on the system. And lastly, the instructions for any given equipment must be followed. So at a very high level, that's what we do to reduce risk. But in this session, we're really focusing on how that's related to variable speed drives. So let's look at some typical ways of protection when applying variable speed drives. First off, a drive itself typically has protection for some conditions. A drive typically protects itself during overload conditions. It also protects itself during output short circuit conditions, and I'll stress the word output there. It also usually protects motors. But what it typically does not protect is itself from internal short circuits in its own DC bus. It also typically does not protect external conductors, nor multiple motors connected to a single drive, typically. There are some exceptions where there are some large and specialty drives that include built-in short circuit protection for the internals of the drive. And also the other exception would be that UL is presently considering for the future that the drive would have a means of protecting output conductors. But that again is for the future. So what generally happens is, in most cases, there is something that's required besides the drive itself, to protect itself. And that's known as an overcurrent protective device, and which is a fancy term for typically breakers and fuses. Now, it's helpful to look at a few common protection scenarios. Let's first look at a feeder that's serving multiple branches. And off of that feeder, typically there's an overcurrent protective device, being again a breaker or a fuse generally, that's protecting the wiring. In some cases, if that device is chosen properly, it has the ability to also protect the drive. But that's not always the case. So let's look at another case in which the overcurrent protective device is chosen, but according to the drive instructions, it's not the right device to protect the drive. So in that case, an additional or supplemental protection device is required to protect the drive. So now we know that drives nearly always require an external protective device, and sometimes, but not always, can be protected by the same devices that are protecting the branch circuit wiring. Before getting more specific and diving into how UL is related to this, I want to take a few minutes to make sure we're all on the same page with some terminology. The terms short circuit current, or SCCR, and amps interrupting capacity, these two terms are related, but definitely different. Short circuit current rating is really the ability to withstand. And it's for components or assemblies, their ability to withstand when protected by protective devices based on a fire and shock hazard external to the enclosure. And the rating for these devices, for short circuit current rating, is typically kiloamps and never amps interrupting capacity for withstand. Now let's talk about amps interrupting capacity, AIC. Amps interrupting capacity is really the maximum short circuit current that a protective device can safely interrupt. Okay, so we're talking about devices like fuses and breakers, overcurrent protective devices. Okay, and that's the key word there, because on the right-hand side, you can see these devices are capable of interrupting. On the left-hand side, those devices are only capable of withstanding. That's a key differentiator here on what we call SCCR kind of systems and devices versus devices that actually have an interrupting capacity on the right. And of course, on the right-hand side, those devices are always have an AIC rating, interrupting rating. Now, just remember, SCCR is what something can withstand, and AIC is only for devices meant to interrupt. But often, SCCR and AIC rated devices are combined. In such cases, we wind up with a withstand or SCCR capability based on the combination of these devices. Let's take a look at some examples. In this example here, we have a drive that's published with a maximum capability of 100,000 amps when used with a protective device. But in this case, the protective device that's being used on the input has an interrupting capacity of only 25,000 amps. So in the end, we have a withstand or SCCR capability of only 25,000 amps. So it's the lesser of the two. Let's take another look at another example. Here we've got both devices that are rated at 100,000 amps. Both the drive has a 100,000 amp SCCR, and the breaker or fuse has 100,000 amps interrupting capacity. So in this case, the total system has a combination withstand rating of 100,000 amps. Let's look at one more. In this case, we've got a drive that has a lesser withstand capability. It can only withstand a maximum of 31,000 amps when used with a protective device. But yet we're feeding it with a protective device that has a interrupting capacity of 100,000 amps. In that case, still, it's the lesser of the two for the combination withstand rating. Okay, so quite simply, the FCCR becomes the lowest of the component ratings. Now with that foundation, we're more prepared to look at how UL standards and testing have evolved relative to drive protection. As most of us know, system designers and installers must follow instructions by installing approved protective devices. They also obviously want to use common inexpensive devices. What you may not know is that UL approval actually requires destructive testing. And it has become much more difficult than in the past. And also results are often different between what we would call exposed applications, such as a drive that's mounted directly out in the open, and enclosed applications, where a drive is mounted inside of a supplementary enclosure. So we're going to go into some detail, but related to this, the path to UL approval has definitely changed over the years. And in the past, drive manufacturers worked hard to provide customers with very desirable or forgiving protection solutions along with its UL listing. But things are changing as we move into the future. And existing product that's been in the market for quite some time is grandfathered unless there are major changes to the product that UL cares about. But newly designed product, in this case, there's many limitations based on the installation type and the required withstand rating or SCCR rating. Like many other product categories, UL has specific standards for power conversion equipment like drives, and the evolution of requirements has certainly affected these standards. For decades, UL 508C has been the standard for which all drive suppliers have been evaluated against. As some of you know, UL 508C has been replaced with a different standard going forward. So as of February of last year, UL is no longer accepting any new applications for drive products under 508C. However, they are allowing existing projects to be completed. Now, existing products do remain valid, and they don't need to be investigated to the new standard unless, as I mentioned before, there were significant design changes in those products. Then they would have to be reevaluated to the new standard. One of the things that we're going to go into further here, because the UL standards cover many, many things, but the thing that's most pertinent here and the biggest change over the years that's changed the way drives need to be applied is one particular part of the UL standard known as the component breakdown testing. And this component breakdown testing is actually destructive testing. So one of the things that a drive supplier has to do is pass a test where the DC rectifier is shorted. Another and more catastrophic test is where the capacitors inside of the drive actually have to be shorted. And even prior to moving to the new standard, throughout the years, this test has actually changed and it's gotten much more stringent over the years, even before moving to the new standard. So that's an important point. Now, the new standard, 61800-5-1, which may look familiar to some of you because there are European standards with the same number. It's really a standard that's harmonized between 508C and the European standard, but it's actually a superset of the two. So it's not the same as what you might see in IEC versions of that same number. And this was published all the way back in June of 2012. And again, though, we are subject to the component breakdown testing, which is a very severe test. And not only did that testing become more severe under 508C, it's become even much more challenging under the new standard, in the fact that to attain the high withstand ratings, such as 100,000 amps, drive manufacturers actually have to do that now in a high current lab with calibrated fuses. So it definitely has gotten more challenging to do. There are many drive products on the market for which 508C approval will remain indefinitely. Depending on the project timing, newly released products can be either, but most new releases will have the new standard, that is 5-1 approval. Additionally, it's very likely to see some existing 508C products get recertified to the new standard. Okay, now let's refocus on this component breakdown testing, because that is what has changed the game in the biggest way. The purpose of the component breakdown test is to see how safe or how dangerous the product is when internal short circuits are created. That's very different than creating external shorts for which a drive generally can protect itself against. During this destructive testing, internal short circuits, which are explosive and damaging, are purposely created. And the test result greatly depends on the type of drive construction, the available fault current that we talked about before, and the type of input protective device used. And it's most difficult to pass this test when the drive is exposed to the customer environment, like a standalone application. Easier to pass when the drive is enclosed within a supplemental enclosure. Before going further, let's briefly review a typical power design for a variable speed drive. On the left, we have the rectifier section, which converts AC to DC. In the middle, we have what's called the DC bus or DC link, which filters and actually stores energy. And on the right, we have the inverter section, which converts the DC back into variable AC so that the motor can be controlled. Now, although the DC link often has inductance and multiple capacitors in series parallel combinations, before moving on, just remember that if something bad happens in the DC link or on the DC bus, there's potential for large amounts of energy to come from the power source straight through the rectifier. Let's keep that in mind. Now, remembering that basic diagram, let's discuss the component breakdown test just a little more. As we discussed before, UL now requires drive manufacturers to purposely create short circuits. So let's look at the 240 volt class of drives and the 480 volt class of drives separately. On a 240 volt class of drive, the rectified value, in other words, the bus voltage, is around 325 volts. And generally we have capacitors in parallel, many of them, but not in series. And we use 400 volt capacitors in that circuit. So that 325 volt bus is no problem for a 400 volt capacitor. And in fact, when we simulate a short across it, the capacitor likes it even more. It's very happy. So we're taking it from an average stress down to zero stress. And of course, there's no issue there. And as I mentioned, those are 400 volt rated capacitors that are used. But let's look at the case of a 480 volt drive. Now the rectified value there for the DC bus is 650 volts, but we're using those same 400 volt capacitors, but we use two of them in series. This is the typical architecture of a drive. And when we use two of them in series, the voltage is being shared between those two capacitors. So when we simulate a short circuit across one of the capacitors, Again, that capacitor has no problem. We're taking it from an average stress situation down to zero stress. But what happens there is that that capacitor isn't taking on its responsibility anymore. And now all of that voltage, that 650 volts, is being applied across that other capacitor that's only meant for 400 volts. So the result is not very good at all. That capacitor hates having that, and the result is explosive. So it's no surprise that a drive will be severely damaged by this test. That's expected. What we, and of course UL, care about is whether or not it's possible to cause physical harm. So how is the test generally set up, and what is the pass-fail criteria? Well, the test condition is such that the equipment under test must be surrounded with surgical cotton. And for a drive itself, that cotton directly surrounds the drive. But for a drive installed in a cabinet, the cotton surrounds the cabinet rather than the drive inside the cabinet. And a test is considered a fail when the surrounding cotton ignites, when there is molten metal on the exterior, when a door or cover is blown off, when a ground connection is blown, or when a touch surface becomes live. Now, this is most difficult to pass when a drive is mounted standalone by itself. However, based on the type of protective device used, there are solutions for this type of installation. This following chart summarizes the typical results from many common installation types with different protective devices. In the left column, you'll notice two installation types, that being enclosed and standalone, where the drives are completely exposed. Across the top row, we have semiconductor fuses, which are the fastest acting and offer the best protection. In the middle column, we have conventional fuses, such as class CC, JRT, and these are also adequate protection in many cases. And then in the far right column, we have molded case circuit breakers and RK fuses, which are the slowest acting devices and thus have more limitations of use. But please note that this chart is only typical, and not only must you absolutely pay attention to product instructions for individual products, but also differences across models within a single product family. On the next slide, I'm going to show you something a little more visual that represents this chart of typical results. Let's first look at two main cases of a standalone drive. That is, a drive that's not mounted in another enclosure. So in one case, we have a drive that's protected by fuses, and in another case, we have a drive that's protected exclusively by a circuit breaker. So the result is that the drive that's protected by fuses, the standalone drive mounted out in the open, no problem, the fuses are adequate. But that same drive mounted out in the open, protected by a circuit breaker, typically does not pass the test according to UL. And I say typically. Now let's consider those same kinds of protection, but with a supplemental enclosure. In other words, the drives are mounted inside of an enclosure. In that case, both fuses and circuit breaker by itself actually passes the test. It's often considered approved UL type of protection. And lastly, let's talk about a variation of that in which the drives are mounted in an enclosure, but those protective devices are mounted somewhere else. And it's very similar that both of those situations pass the test. There's one exception, however, with UL, and that is if the fuses being used are semiconductor type fuses, UL requires that they actually be located in the same enclosure as the drive. So that's just one caveat there. Again, I want to stress that what's shown here is only typical results. When choosing protection according to drive supplier's instructions, you will definitely find variation and detail that you need to be aware of. We're going to take a look at a quick example of such instructions from a drive supplier, but before we do that, I just want to recap the impact of UL. First of all, UL requires this destructive testing. The test result is greatly affected by the choice of the protective device. The old standard, UL 508C, has even become much more challenging over the years, even prior to moving to the new standard. And that all new projects are moving towards 61800-5-1. In fact, they are required new projects starting as of February of last year. And remember now that 508C products remain valid. So when we see the words that 508C has been withdrawn, it's only been withdrawn for new projects. Those existing 508C products remain valid indefinitely. As I mentioned, there's been major changes to 508C, and or I should say that major changes to a product could require that products that are presently listed under 508C could be forced into the new standard because there may be design changes to those products. And lastly, the new standard, 5-1, those listed products will likely have more use limits when it comes to protective devices and things like ability for withstand rating. Also, capabilities are becoming different between exposed and enclosed applications. So be aware that when you're choosing a protective device, know whether your application is standalone or whether it's a drive that's installed in a supplementary enclosure. There is a difference there in what can be used. And of course, where you'll find that is in the individual product instructions from drive suppliers. So pay attention to all these differences and caveats. As I just mentioned a moment ago, we will now look at example of manufacturer's instructions. So let's do that. This is such an example, but each drive supplier has their own way of organizing data and footnoting. This is just one example. As you can see in this example, there are multiple choices for protective devices. First, notice in this case that fuses can be used without restriction, including the case of a standalone installation. In other words, no supplemental enclosure. But secondly, notice that some devices have limitations of use. In this case, the devices inside the red box can be used only when the drive is mounted in an enclosure. However, circuit breakers and RK fuses have the additional requirement of minimum enclosure size, and this is stated so in these instructions. You must always pay attention to the fine print and may find differences between drive sizes and voltages. Again, this is just one example. You must use specific supplier instructions. Lastly, you will often find differences between UL compliant and non-UL compliant installations. These are both often included in instructions because the same product is sold for use worldwide. Now that actually completes all of our related topics for today, but I want to leave you with the following key takeaways. In summary, equipment withstand or short circuit current rating is very important and should be selected based on available fault current. Most drives require a separate protective device according to manufacturer instructions and of course UL. And UL approval has become much more rigorous even prior to the new standard, changing the way drives can be applied, such as whether it's enclosed or not, protective device used, the withstand rating needed, the voltage class, etc. And UL 508C products remain valid indefinitely. Please remember this. But future products will all be listed to the new standard, that being UL 61800-5-1. That nearly completes our presentation today. Before I hand it back to Kevin for open Q&A, I'm going to address a few common questions. First of all, question number one, many customers do not know their available fault current at a point of equipment connection and sometimes unable to determine it. For these cases, what is recommended and whose responsibility does it become? Well, it is the installer's responsibility to install equipment with adequate withstand rating. And an owner will often hold the equipment specifier responsible if on-site equipment changes need to be made. But a specifier can inform an owner of withstand choices that are available for equipment to purchase, so that then the equipment selection becomes the responsibility of the owner. Next question. Is it good practice to design panels with a 65,000 amp withstand rating? Well, the best practice is to determine the available fault current and then choose equipment. But when designing standard panels with unknown destination, it's unlikely to be connected to systems with available fault current greater than 65,000 amps. However, remember, some customers specify 100,000 amps regardless of their available fault current. Next question. If the drive UL standard is changing from the old standard 508C to the new standard 5-1, what effect does that have on UL 508A, which is the panel standard? Well, 508A, not to be confused with 508C, is the standard for industrial control panels, and it is here to stay. At this time, there is no replacement for the panel standard 508A. So drives listed under both the old standard and the new standard can be used in 508A listed panels. Next question. How are UL, the National Electric Code, and the National Fire and Protection Agency related to arc flash? Well, UL requires that listed equipment include clearly stated withstand capability, or SCCR, which is also required for NEC installations. And customers must follow OSHA regulations, but if violations are found, OSHA references NFPA 70E, which covers arc flash requirements, including things like personal protective equipment and calculation of incident energy levels. All right, that covers a few common questions and completes our agenda. Now back to Kevin.
Well, thanks so much, Steve, for what was really a truly informative presentation. We look forward to seeing you in the live session immediately following. Be sure and have your questions ready. Thanks for joining us, and we hope the information provided will suit your purposes.